I'm very pleased to be here with you. I'm also very thankful to all of you that decided to join at least this first lecture. So as you know, the University of Seville is doing a great effort to not only organize activities in-house, but also to make them open and freely available to all the mathematical community. So I'm very, very pleased to be here with them. So Enrique Fernández-Cara, so Enrique 1, I am Enrique 2. Enrique Fernández-Cara is an old friend and also a former collaborator. We have written some papers that, by the way, in principle were oriented to the classical topics of control of partial differential equations, but that are also very much aligned with the present priorities and objectives in the field of machine learning. So this is where we stand now. So something I wanted also to ask you is, please, for me and for everyone lecturing a course like this, it's always hard to guess what the attendees have in mind. So if you please don't hesitate to ask questions, put comments on the chat about what I'm lecturing, or maybe also topics that you would like to see treated. Because it happens very often that it's only after the end of the course that the professor gets the feedback and the student says, or the attendee says, "Oh, your course was very interesting, but I was expecting that you will talk about this and you didn't." Well, then it's too late. Okay, so try please to anticipate so that we have time in the 3 sessions we will be meeting to address these other topics too. Okay, so this is very much where we stand. I mean, to some extent, of course, there is much more. There are many more applications and also scientific breakthrough developments in this area. You have seen that the Nobel Prize in Physics was allocated precisely to physicists and computer sciences working in the development of new tools of artificial intelligence with important applications like the unfolding of proteins. Okay, but for those like me that are new or relatively new in this topic, when I observe, this is what I see. So I see on one hand certainly ChatGPT. There is no doubt. I mean, ChatGPT is like Google appeared like in year 2000. And before that, there were personal computers and email. So ChatGPT appeared together with some other large language models, and this will stay. So what is ChatGPT? Well, is the union of a number of things, I will say. Is the union of the Wikipedia, because ChatGPT knows everything that has been published on it. Is the union of maybe also Google search, right? So it's able to search everywhere to gather information, but it's more because it's also generative, right? So actually the acronym is ChatGPT, G for generative, P for pre-trained. So it means that we have built a virtual world, purely synthetic, living on computers that have read and seen all the images and read all the texts that are available. And because they have memorized all this, when you ask a question, when you input a prompt, and I ask something like, can you please tell me what is the state of the art in control theory, or what are the early origins of the mathematical control theory, then ChatGPT instantaneously will be able to provide you with a response, right? So for instance, if I just do it online with you, I was doing it this morning in class. Can you see now? I think you can see now ChatGPT here, right? You see it? You see the ChatGPT window, right? So if I ask, can you please tell me about the origins of control theory? So by the way, we have a text written with Enrique Fernández-Cara 20 years ago, precisely on the history of control theory. But at that time, there was no ChatGPT. There was a lot of work that we have to put reading many papers and many books in order to, during months of work, build something that now ChatGPT does in a few seconds. Hopefully, we added some value to the text with respect to what ChatGPT does nowadays, but it's extremely impressive. You see that the answer is already there. It says, control theory has its roots in the fields of mathematics, engineering, and physics with significant contributions spanning centuries. It focuses on how systems, particularly dynamics one, can be regulated and made stable, often using feedback loops. So then you see here early foundations. So the James Watt centrifugal governor in the late 18th century, that was probably the main engine of the Industrial Revolution. The mathematical formulation by Lord Maxwell about the dynamical behavior of the governor mechanism. It took, 80 years from the invention of the governor, the gadget, the device, 80 years until Lord Maxwell, the one who launched and who was the founder of the theory of electromagnetism, was able to analyze from a mathematical perspective the behavior of the governor. This is very much related to understanding the decay rates of dissipative harmonic oscillators, right? Because there is some dissipation of the system is rotating, so it's very much like an harmonic oscillator with damping. And even the engineers that were designing these devices were not understanding well why sometimes it was working better than some others. And it was very much Lord Maxwell who observed, be careful, because for the damp harmonic oscillator, the decay rate of solutions is not monotonic with respect to the amount of damping. So if you put more damping on the system, it could be that the response is slowed down, right? So this is like, when you are building IKEA furniture, if you press too hard, maybe you don't get better results because it will simply, the junction will break, and then, you will not have any chance of putting it together anymore. Okay? And then it talks here about controls in process engineering, the birth of modern control theory with the contributions of Norbert Wiener and cybernetics in the 40s, and a lot of things. So it's impressive. So what took months to Enrique and I to write a text on the early history of mathematical control theory, now ChatGPT does it essentially instantaneously without any effort. But you see, ChatGPT, as I said, is a virtual world that has been created by reading all the existing text and all the existing images. And links have been established between one and the other. Of course, you need to put links if you want that, ChatGPT is able to do what we humans do. Because, if I will try to do the same myself, what I will do? I will, before ChatGPT, so 2 years ago, what I will do is say, okay, control theory, I will write control theory Wikipedia. Okay, so then I have 40 languages for this page. I keep it in English. So it says control theory is a field of control engineering and applied mathematics, stability, optimality. And then by clicking, I see Lord Maxwell here. I see other links with operation research. I see here the centrifugal governor. I see even a drawing. But you see, it's on me to click again and again and again, and eventually, after a number of clicks, go back. Because if I now want to know more about the centrifugal governor, now I am on the centrifugal governor. It explains how it was, why it was designed in order to, regulate, for instance, windmills, in order to keep a constant velocity of rotation, or the steam H in order to keep pressure on the steam engine of the locomotives constant, and so on. Maybe here later I will, I see mathematicians and physicists like Huygens, Maxwell, and so on. But it's very easy to get lost, right? So maybe here you see even Bellman, right? Much more recently, 20th century, about the developments in control theory, and so you see here the paper by Maxwell on governors, written in '68. Then I can even have a look to the original paper by Maxwell. So this is fantastic. So I see the text of Maxwell, but you see that I'm getting lost. I'm getting lost. If I want to go back to control theory, I have to click twice backwards. Now I am back in control theory, and now I can try to explore a different path. For instance, what is the understanding of optimality? What does optimality in control theory mean? Well, it means something very much related to extremality, to extremals, like minima and maxima in the calculus of variations, right? And then I can go through this, and then I see names like Pontryagin, Bellman. Okay, that's fantastic. Hamilton-Jacobi-Bellman equation. I see problems formulated, constraints, unilateral constraints, endpoint conditions, Lagrangians, linear quadratic regulator. I see many things, but again, it's very easy to get lost. So what ChatGPT does, because it has been pre-trained, all these connections are built in, and somehow whenever you do a prompt, ChatGPT will offer you the menu. It's like you go to a restaurant where the offer is huge. You have to go through this menu. It will take you hours to read all the dishes. You rather ask to ChatGPT, please compose a menu for me, taking into account that I like this and that, that I am vegetarian, or I drink wine, but I don't drink beer. And then you will get the menu offer for you, composed for you. So here the same with ChatGPT. It's amazing, right? But there are also some risks. So if I go back to ChatGPT, I was doing this test this morning in the context of control. I said, can you please give me the basic references on waves control of waves. So this is, of course, one of the topics of application of control theory. It can be acoustic waves, so noise reduction, something that is so important. We are very pleased to be in this nice Zoom link offered by the University of Seville. There is no noise. If there was noise, it would not be so pleasant to be neither lecturing nor listening the lectures. Okay, so here I have, but it could be also oceanic waves. It will be tsunami control or any other kind of waves, right? It can be also related to thinking on infectious diseases like COVID. It was a new wave incoming, right? One after the other, okay? So now it says that I already used too much of ChatGPT. It's inviting me to pay for ChatGPT 4. But I continue using the free one. So here you see some, and then it tells you some books, right? Some references. But you see, the risk is, this happened this morning to me, when you ask for some of these references, the risk is that some of these references might not exist. Why? Because ChatGPT is generative. So ChatGPT is not only a search engine that is able to explore the existing bibliometric resources and then choosing and composing the best menu for you out of it, but is operating in a probabilistic manner, the same way we humans follow our intuition to choose one path or another. And because of this, there is no guarantee that these bibliographical references exist. So we can check. Maybe we are lucky with this one. So if I open here Google Scholar and I type this one, okay, so this one seems to exist, but generally speaking, is the probability that ChatGPT gives you a fake reference is also very high, and therefore you have to be very careful because it has this generative capacity. Some people admire it because you can ask ChatGPT, can you draw the painting of children playing in the beaches in the south of Spain on a sunny day with huge waves and surfers catching waves and so on, and you will get immediately a portrait painted by ChatGPT. So it's generative, it's fascinating, but you don't want ChatGPT to be too generative, in particular when you are building a mathematical bibliography. For this, you better use Google Scholar or even better Math.net, okay? Anyhow, ChatGPT is there, large language models are there, and this is probably the best proof of how efficiently this field of artificial intelligence and machine learning is evolving, okay? Okay, so now you see on the top left, you see a very modern scientific development in which you combine classical applied mathematics and machine learning to build what is called a digital twin. Right? So digital twin is like turbulence. So nobody knows how to define it, but we all know more or less what it is, right? So what is a digital twin? Well, a digital twin is a real-time computational environment in which you can track the real-time evolution of a system, in which you can feed the data, integrate the information provided by data. You can make decisions, feedback control. You can decide about the regulation of the system in real time. You can continue capturing information out of the system so that you can better decide. This is very much the concept of predictive control, right? So even though normally control theory is formulated on the basis that we have a system and then we compute the control for that system, in practice it doesn't work like this. We have a system that is likely to approximate well reality. We control the system. We see what the response of the system to our control is, and by learning out of this input-output box, not only you can make your next decisions better, but you can also enrich and improve your system. So this is why whenever we walk in a city, we learn, and we need less and less the map, and our brain is, getting new information, and then we can maybe use the map in order to discover new spots and so on. So this is model predictive control, which is very close to reinforcement learning. Reinforcement learning is something like control and inverse problems simultaneously, right? So if we lecture to mathematical, in a mathematics master, in applied mathematics master, we will say, oh, there is mechanics, there is functional analysis. You merge all these, there is partial differential equations, then there is numerical analysis, and then there are other side topics like optimal control or inverse problems, where in inverse problems, what you aim is to learn the coefficients, the nonlinearity, the details of a given class of systems out of measurements done on field through sensors and different data sets and data statistics. So this is what inverse problem is. And normally people will tell you, no, I do inverse problems, but I don't do control theory. The one doing control theory will tell you, okay, if you give me the system, then I will compute the control for you. But as I said, in practice, things are not that way. You have to control a system that you don't know completely. But while acting on the system, because you are getting new information out of the input-output map, you are learning about the system. So you are concatenating in a zigzag manner. With one hand, you are learning about the system. With the other, you are controlling the system. And then whenever you control, there is new information incoming out of the output of the system so that you can learn better. And because you have learned better the system, of course, you can refine on your action, right? And this is how things operate. Otherwise, you will be offered a new personal computer to start working. Before turning the computer on, you will read 500 pages of instructions books, and this is something we never do. We know basically how our computer operates. If you offer me a new one, I will start operating and learning little by little how nicely it's doing the old task and discovering new tasks. This is reinforcement learning or model predictive control. And this is now a paradigm that is very much being employed in science because there are challenging applications like fusion plasma, on which research has been ongoing for decades now. But despite of the efforts of multidisciplinary teams of scientists working in this field, the application is so complex that we cannot manage to do everything only with the classical tools of applied mathematics. So next Thursday, for instance, in our group, we are running a seminar in our mod center here that you are also invited to join by Paolo Zunino from Milano Politecnico de Milano. He's precisely lecturing on how to combine classical computational mathematics and machine learning tools in order to tackle more ambitious applications, both in engineering and also in biomedicine. So this is a typical application. The process of plasma fusion is so complex that you cannot expect to gain a complete understanding of it simply because you write down very sophisticated PDs coming from mechanics, and then you will apply a lot of functional analysis, existence and uniqueness theorems, and even classical, say, tools in numerical mathematics and in control theory. You need to enrich this process learning from data. So there are plenty of sensors placed in these big infrastructures that are feeding information, and this information is integrated in the model very often through artificial models built on the basis of data and very much like the large language model inspired on neural network ansatz. And then the third example I brought here at the bottom to the left is precisely another application of reinforcement learning in which people have developed new computational methods in order to multiply big matrices. We all know how to multiply matrices. Of course, if you ask me to multiply a matrix 2 by 2, I can do it. I mean, matrices 2 by 2 is not that hard, right? So it's A11 times B11 plus A12 times B21 and so on. I can do it. If the matrix is 3 by 3, I can still do it. But if you give me a matrix, say 156 times 156, I don't want to do this. However, multiplying matrices is fundamental in computational mathematics because even if originally problems are very nonlinear and very infinite dimensional, in the end we have to reduce everything to the finite dimensional context. Nonlinear problems are solved iterating by linearization. So in the end, everything is about multiplying and adding big vectors and big matrices. So matrix multiplications is the key, and accelerating the ways we multiply matrices is one of the fundamental problems to be tackled if we want to improve our computational methodologies. And you see that surprisingly, right, we develop traditional mathematics like calculus, algebra, to get very, very, very far, right? We are able to simulate 3D, airfoils, and with this we have developed the most modern generation of contemporary aircrafts and so on. We got that far, But still, even when we thought that computational mathematics was over, and then we enter into the new generation of artificial intelligence, say, tools to tackle other applications, people realize, listen, the same reinforcement learning that was employed in order to build the machine, the computer that was able to, to defeat Kasparov in chess, or the AlphaGo machine that was able to win to the, on the game with the world championship champion in Go, the same algorithms that can be used for these games can also be used for multiplying matrices more efficiently. And then you go to the very beginning, because you can revise all the computational mathematics and realize that you can do it better, faster, and ambitioning higher dimensional systems. So now we are on a loop. So artificial intelligence is not coming here only in order to create a new virtual world that is separate from the rest. No, it's part of our, say, science and technology system from the very beginning. This is like, ChatGPT is not only here in order to, to answer to tricky questions we can think of. No, it's going to change the way we work, the way we teach, okay? And I refer to ChatGPT, but I should actually refer in general to the existing large language models that, as you know, they are rapidly evolving and also multiplying. Okay, so now, good. So regardless whether you are an expert in machine learning, you are a more traditional applied mathematics as a mathematician as we are, you are a control theorist or a control engineer, you can wonder, and then what can we do with all this? So there are many different questions. Nowadays, there is a huge interest on the interface between machine learning and applied mathematics. And I think it's good to put some order on the kind of classify the kind of questions that one can tackle. And here I brought 3 different topics for you that oftentimes are a bit like mixed up, right? When someone tells you, no, I'm working in machine learning for PDEs. Well, what does it mean, right? So, and it might mean different things. So one of the possible meanings is related to question number 1, is why it works. So how can it be that we were able to create an artificial, say, system, because it's not, right? So when we are modeling, studying Navier-Stokes equation, we are trying to mimic the wind, or we are mimicking the rivers or the ocean, or we are mimicking the human blood flowing on our cardiovascular system. So artificial intelligence, large language models, is something different, because we have created a completely virtual world, right? It's true that we were inspired in nature, we were inspired in the human brain. We have used all the computational power that mathematicians and scientists have developed during, many centuries. Yet it's totally artificial, but it works pretty well. You have seen that how rapidly we got the summary of the state of the art or the origins in control theory. So why does it work? Is there some mathematical explanation of this? What are the mathematics we need to explain this? And is this a question for what? For probabilists, in order to determine with which probability the answer provided by ChatGPT is going to be right or wrong? Or is this a question for numerical analysts that are used to deal with the complexity and the convergence of algorithms? Or is maybe related to people working in functional analysis and the geometry of high-dimensional spaces where there are paradoxes like the concentration of measure and so on? Is this related to large language models as well? Because they are so huge, maybe high-dimensional functional analysis is relevant. Is this related to control theory? as we will see, closely related to the origins of artificial intelligence? Is this related to dynamical systems? Because after all, we ask one question and we get an answer. Is it related to the stability of this dynamical system? Because you can check yourself. You ask ChatGPT a question on the topic you like, and then you ask it again later, a few hours later, and you will get different answers. Maybe you didn't ask the question in the same way. Maybe in the morning you said please, and in the evening you are tired and you don't say please anymore. And this already, the prompt you introduce in the system changes, and therefore the output of ChatGPT changes as well. Is this related, therefore, with the stability of dynamical systems? So you see that information theory, geometry, dynamical systems, control, numerical analysis, in different applications when we are dealing with large language model with image processing, is this related to Fourier analysis, wavelets? So there is room for everyone in every mathematical discipline to think on this fundamental question. Why does it work? Now, if you are, as Enrique and I are people trained in the classical paradigm of applied mathematics, in which there was, as I said, mechanics, PDEs, functional analysis, solvability of PDEs, and then a posteriori maybe numerical analysis, inverse problems and control, and so on. Then the second natural question is, now that all these tools are available, neural network approximations, large language models, so depending on whether you want to use neural network approximations from very scratch, or you want to really use the already very sophisticated available large language models as a search space for looking for the solutions of the PDE, can I use these machine learning tools in order to solve PDEs, or at least help solving PDEs? How can I add the added capacity that these machine learning tools provide to traditional numerical mathematics? This is the second topic. And then there is a third topic, which is very much related to this application I have mentioned of plasma physics, is, listen, until now, we were modeling physics out of continuum mechanics, classical mechanics and continuum mechanics. So if you tell me about, the building I am here, so this is the Felix Klein building. As you know, Felix Klein, very celebrated mathematician for his contributions to hyperbolic geometry. He's the one who built this Felix Klein bottle, right? So so you see the Klein bottle here. So this is like a three-dimensional Moebius band. So it's a bottle without any opening. So it's very pretty, but you cannot use it, right? Because you will never be able to fill it of liquid. And if it were full, then you will never be able to drink out of it. So Felix Klein was professor here in Erlangen in the end of the 19th century. And this is why the building I occupy we are occupying here, the math department is located, is named after him, okay? So if you ask a question about, where I am now, sorry. No, not this. If you ask a question about, sorry, one more technical thing here. Okay. Now you should be able to see them. I think you see the slides again. So if you ask a question about how well this building is built, how will it resist strong winds, how will it, survive in case there was an earthquake and so on, well, I know this is very much about elasticity. So I will look to the, to the elasticity equations. Maybe I have to deal with shell model. Walls are like shells, so interconnected shells. There is plenty of literature, and then I could compute the deformations, at least build a computational environment in which I could test how this building, given his geometry and dimensions and the materials were used and the land in which it is, built, how it will resist, the impact of winds and seismic waves. So this was the traditional way of doing. And if you are asked about pollution in the lake of your town, then you will think immediately on, say, maybe Navier-Stokes equation or shallow water equations in case the lake is not very deep and so on. You have, in mechanics, you have this collection of models that are adapted to the main applications you can encounter in sciences and engineering. But as we said, nowadays, very often, we are facing so sophisticated applications that we will not be able to tackle them only based on the modeling paradigm that mechanics offers. On the other hand, we are living in the age of information theory. We have plenty of information available. We have plenty of data available. We have even many gadgets that nowadays sensors, technology is getting cheap. So you can place many sensors for a very low cost. They will provide you plenty of added information. And therefore, there is the need of developing a new field of applied mathematics that I like to call PDE plus D. Is PDE plus data, is to increase all we have achieved with partial differential equations, adding this extra layer of what, data and information based on artificial intelligence can provide, okay? So you see three different ways of dealing in this, working in this interface between applied math and machine learning. The first one is, why does it work? You don't need to employ it for any specific application. You don't need to do anything new. Just try to understand what machine learning is doing and try to explain in mathematical terms why this artificial construction works so well and is able to answer to many of the questions we as human beings can be interested in. First topic. Second topic, from a classical perspective of PDEs, we are not abandoning PDEs. We will remain in the universe of PDEs. We are only interested on trying to understand whether, these new tools of machine learning can help us understanding better PDEs, approximating its solutions in a more accurate manner. And the third dimension is whether we can contribute to generate this new scientific paradigm, which is both model-driven, but also very much inspired on the extra information that data provide this field of PDE plus D, okay? So let me then, I will try to briefly, of course, each of these questions will be, will deserve a course, will deserve a live. There are teams working in each of these areas doing magnificent things. I will not be able to tell you about the state of the art in all these fantastic, recent developments. I can only give you some hints of my take to this, and maybe this inspires you on, developing your own perspective on your own journey. So first question, how does it work? As we have said, we have created a new artificial wall. It's very much like drawn here at the bottom. Is like a large network, right? That you can basically represent by a matrix, like a, if we will build, we are now like 80 people in this group, so we could build a chat, a WhatsApp group, so with 80 nodes, and then we could very easily represent the activity on this chat by a matrix, 80 by 80 matrix. So if you see that, that there is a 0 on the entry 1, 9, it means that, the number 1 in this list of this chat, maybe in alphabetical order, the number 1 is not sending messages to 10. But maybe you go to A10-1, and you see that despite of the fact that 1 is not sending messages to 10, 10 is sending plenty of messages to 1. So you see a 9, right? So you, in a connectivity matrix, you will immediately have a rapid visualization of how intense is this network operating. You could see a very dense network when, all these numbers in this matrix are huge, right? While you will see that the matrix is very scarce, very full of zeros, it will mean that although the network is huge, then the level of communication is very weak, right? And in this way, you could model the internet, you could model any social network, any networking interaction. This could be also the network of, I don't know, the electric distribution in Spain or in Germany, or it could be the road. You can use this graph idea, right, in very various manners. And we understand that somehow in this graph, we like to see it horizontally oriented. So for us, the depth will be, we will see, when we see this graph oriented horizontally, we see it layer by layer. When we say layer by layer, it means that every column is one layer. Layer by layer means that we are seeing this graph as a time discrete dynamical system. So that basically, when I ask something to ChatGPT, I am giving, the values of the nodes of the first column, and then I will observe how this information evolves along the network until I get the answer. So what ChatGPT does is I ask, can you please tell me about the origins of control theory? And then I get the 2 pages text that you have seen as an output after, the information travels along this network horizontally, layer by layer. And then you see that in every layer there is a number of neurons, right? You can make it taller or you can make it narrower. It might be always the same, we call it width, right? So we say that how many steps I am doing on this dynamical system is what we call depth, but width is how tall these columns are, how many neurons I am accumulating. So of course, the more is the width and the more is the depth, the more neurons you have, and therefore there is also more memory in order to learn about all these Wikipedia pages and so on, right? Okay, and then there are connections. Recall the terminology in ChatGPT, G for generative, and PT is for pre-trained. Somehow this network has learned, has digested all the textbooks in the Wikipedia, right? Has read the Bible, has read El Quijote, has read everything in order to, build this network in which the connections have also been already established, right? And then there is, as indicated on the left with this red arrow, there is this rectified linear unit. There is this very elementary nonlinear function that, in PDEs we call it the positive part. And it's very much used, for instance, for Laplace, for elliptic and parabolic problems to prove the maximum principle, right? If U is the weak solution given by Las-Greenland, if U is in H10 omega, then U plus is in H10 omega, and it's a very good candidate to be used as test function so that you can prove, for instance, that when the applied force is positive, the solution is positive. Oh, but here the use is totally different. So the ReLU is just a one-dimensional Lipschitz function, piecewise linear, which is 0 to the left and is linear to the right. And the ReLU is here simply in order to mimic how the human brain works by, activating some neurons while the other ones are silent. So somehow the ReLU is a nonlinear artifact you definitely need when you are dealing with data, because, the simplest thing you can think of as an exercise in data science will be, okay, I give you, a collection of a basket of plastic balls, like toys for kids. Some of them are white, some others are black, and I tell you, please classify the white balls in this basket, the white basket, and the black balls in this other basket. So you need to discriminate white and black. So this discrimination fact has to be done in a nonlinear manner, saying yes or not, true or fake, white or black. And in order to do that, you need the ReLU, the nonlinear activation function. So you see that artificial intelligence works, machine learning works by building a graph along which we iterate again and again and again, like in a time-discrete dynamical system, right? And there is this nonlinear artifact that allows us to bifurcate left or right, left or right, left or right. Now, this is the architecture of the neural network, which, again, I repeat, is a graph plus the nonlinear activation function. One of the most popular ones is the ReLU. And then on the top, you see the exercise we have to do in order to train the neural network for a specific purpose. So nowadays, this is something that many groups in science and also companies are doing, is what they call the fine-tuning. They take the large language models, the free versions available. Of course, ChatGPT will not release you the full model that they are selling, but there are some simplified versions that are open access. So in your company or in research group, you can download this large language model, install it in your computer, and then fine-tuning for the specific task you are developing. Imagine that you are, I don't know, working in brain cancer, and then you have plenty of images of magnetoresonances of different brains, and you know which one led to diseases development and which ones were healthy and out of risk. And you want to fine-tune the parameters of this large language model in order to tackle this specific application in which you are really focusing and you are an expert on. So you see that nowadays these large language models, freely available, open access, give you the possibility to, instead of starting from scratch yourself, reading books in neural networks and machine learning and building your artificial intelligence model, you start from the very rich model that the large language models offer you, and then you fine-tune eventually by better fitting the parameters and maybe even reducing its dimension possibly, because specific applications don't require all the complexity of a large language model to use it. This is very much what we have been traditionally doing also with, for instance, MATLAB. MATLAB was what? Was a replacement for the other alternative, that is, okay, take your computer and start programming from scratch everything that needs to be done in order to simulate a PDE. To begin with, you have to describe your domain, you have to triangulate your domain, you have to define the mass and rigidity matrices. This will take a lot of work. This is what has been done, for instance, in very successful softwares like Phoenix, right? So start from scratch and build Phoenix as an assistant for computational mathematics. So the same in machine learning, you can start from scratch, or you can start from the large language model and then go down, right? Go up or down, bottom up or top down. But in any case, for the specific application, you have to tune the parameters. The connections between the neurons are there as indicated in the graph. But now, for every specific application, you have to determine how intense these connections are. And the intensity of each of these arrow of these connections is mimicked reproduced here, represented here by the coefficients AJ, WJ, BJ. So AJ, WJ, BJ will become more precise later. By now, let us oversimplify by saying this is simply how much intensity you put in each of the connections, in each of the neurons, okay? And J is just an index that is counting how many neurons there are or how many edges in the connections of the neurons. Doesn't really matter, okay? So AJ, WJ, BJ are the parameters you have to tune. You are going to do it by classical optimization tools. So this is why on the right-hand side, we add a term that is penalizing the size of this coefficient. So to avoid divergence towards infinity, we are guaranteeing coercivity in this optimization problem. Note that we are in finite dimensions, maybe high dimension because there are many neurons, but always finite. So we are dealing with a continuous function in an Euclidean space, a continuous function that I have made coercive because I have added this quadratic penalty term, a la Tikhonov. So the existence of the minimizer is not the problem. But what is the core of the business? The core of the business is that I have a data set, represented by features, for instance, X, J, I, and I have their labels. So I have someone that was kind enough to come to my laboratory and put the colors in, for instance, 100 balls, right? Now that I have labels on 100 items, or I have labels on 100 magnetoresonance outputs in which, the people in my lab were kind enough to go carefully through each of them and say which of them are healthy and put an age, and which of them we anticipate risk of development of some cancer disease, so H and R. So we have the X's are these magnetoresonances, the levels are the Y's, either H or either R. So what we want is to build a mathematical function, this mathematical graph, in which whenever I will input on the left one of these images, one of these X's, on the exit, I will get the correct answer, either H or either R. What is the idea? This is what is called supervised learning. In supervised learning, out of this supervision, out of this exercise where I have 100 magnetoresonances with the correct label, I build this function. This function, which is this mathematical graph that behaves like a time-discrete dynamical system with plenty of nonlinear bifurcations in order to be able to allocate to each of the magnetoresonances the correct either H of R or R. Once this machine, this function, this graph, this dynamical system has been built that correctly operates on these 100 known samples, now I can use it to generalize. And then finally, this is the G of generative of ChatGPT, right? So I'm not doing all this work just to be able to test whether in these 100 magnetoresonances I have the R or the H right. This was already done by the team that was assisting us and was putting the labels correctly. This has been already done. What we want is to learn from this data, build this discrete mathematical nonlinear architecture monster that is able to guess the right R or H for every of the learned data, so that whenever someone comes with a new magnetoresonance, I can feed it to the system as initial datum and see what it comes out. It will come either an R or it will come either an H. Normally, actually, what you get is not an R or an H, but you get a probability of being more likely R than R, and so on. And this is why, oftentimes doctors don't tell you, oh, you are totally safe. No, they tell you, okay, by now you are fine. Please come back in 1 year, right? Because, there is always a non-negligible probability that this, which is healthy today, becomes risky in 1 year. Okay? Now, I very much recommend you to watch these videos in 3 blue, 1 brown. Maybe we will see some of them if we have time. They are very well done, and they tell you basically the mathematics of ChatGPT into some level of detail. There are a few things that I would like to underline at this moment. So first is that the number of parameters in ChatGPT 3, this is the free version, not the paid version, ChatGPT 4, which is much bigger. In the free ChatGPT version, there are 175 billion, 10 to the power 9. So 20 more times than inhabitants in Earth. There are 175 billion parameters, nodes, that are being trained in order to fulfill the task. So it's true, you are solving an optimization problem. The dimension is finite, but the dimension is high. It's 175 billion parameters. Second key issue, therefore, we are facing the course of dimensionality. Now, note that the course of dimensionality, this fact that problems that for us are very elementary, they become simply impossible to be handled even by the biggest computers because of the dimensionality they acquire. This concept of the course of dimensionality was coined by Bellman when dealing with optimal control problems. So he was the one who derived the principle of dynamic programming, who realized that the answer to the control problem is on the solution of the Hamilton-Jacobi equation. But this Hamilton-Jacobi equation has as many dimensions as the dimensions of the finite dimensional system you are trying to control, and therefore the finding the correct solution to Hamilton-Jacobi is so complicated that he coined the concept of course of dimensionality. This is one. And the second one, high dimensionality, course of dimensionality. The second one is the devil of non-convexity. Why? Because even though, you see, in this presentation here, you see like a graph, and everyone thinks on a linear graph. And you see also on the right-hand side on the functional to be minimized, a quadratic term. Because of the intervention of this ReLU activation function, right? The problem there is highly non-convex. Recall that the composition of two convex functions is not convex. Therefore, this problem is non-convex, is the functional in this very high dimensional space is full of critical points. So getting to the minimizer or close to the global minimizer is a huge, computational challenge. And then the last comment I wanted to do here, and then if you don't mind, we stop 2 minutes, so at least to get a glass of water. The last comment I wanted to make here is this was mainly developed by computer scientists. Mathematicians, we did very little, generally speaking, for this field. Percentually, I think this is correct. I don't know the numbers, but probably if you will check, you will see that, these efforts were very much driven by computer scientists, neuroscientists, physicists, and mathematicians were a minority on this, right? Well, of course, we are also less numerous than computer scientists, we know, right? So now there is a point in which there are many instances in which there were very smart ideas that played a fundamental role on the success of these new artificial synthetic technologies. One of them is, listen, okay, assume the machine reads El Quixote. And so what? What do I learn from El Quixote? So you see, when you give me this collection of 100 magnetoresonances with the R of risky or health or H of healthy, clearly I learn something. Because whenever, even myself, without having any clue about the interpretation of magnetoresonances or brain cancer, even myself, without having any clue, if you give me a new magnetoresonance, I will observe the pattern, the geometry, the patterns, the intensity of colors, and so on. I will compare to the other 100, and simply visually, I will be able to establish analogies. So clearly, when you are doing supervised learning so that you have features and you have labels, it's very easy to guess that you are learning. And the more features and more labels you have, the more you learn because you have a better, a richer database to compare, right? Okay? So this is like when looking for the guilty person out of the, the digital prints, right? Okay? Fingerprints. So, of course, the richer is the database, the easier is to find the guilty person out of the fingerprints. Okay? This is why whenever we get an ID, they ask us to do a fingerprint, so that in principle there is one fingerprint per habitant in the world, so that in case they are looking for your fingerprints, they cannot miss it. Okay? That's the idea. So we learn out of a very rich data set, but with entries and outputs, with features and labels. But now, when I let the computer read the El Quixote, okay, there are many words in El Quixote, there are plenty of features, but where are the labels? Where are the labels in El Quixote? So what do you think? Do you have any guess? Maybe you can put a comment on the chat. How can I get labels out of El Quixote? What I see is many words. So I see many features on the left. But how I do generate the labels on the right? Well, what they did is out of a text, they derive the algorithm that is called self-supervised learning. Self-supervised learning roughly means that you take the first word in El Quixote, and then to the first word in El Quixote, you can allocate the second word as being the label. And then you take the first two words of El Quixote, and then you can allocate the third word as being the label. And in this way, you can try to understand also the way human languages, syntaxes, vocabularies are interlaced to build, actual human communication. So self-supervised learning is a way of, in principle, out of a problem in which supervised learning was impossible because the labels were not provided, to invent the labels so that out of this apparently non-supervised learning process, you can generate a supervised learning problem that you can tackle from, with the previous methodology I mentioned, right, in here, but of course, in a giant manner. Okay, good. So I have said more or less how this was done. Take data, put them into a huge graph with this nonlinear function built in, tune the parameters very finely by minimizing high-dimensional non-convex problems, but you can always apply some gradient descent strategy, stochastic gradient descent strategy in case of non-convexity to get something. Of course, you will never get to the global minimizer, but you get something, and then use this as the function, the parameters of the function that will be used for generalization. As I have told you this morning, this is what ChatGPT does. You generate, you generalize, But sometimes also you invade fake things like non-existing mathematical references. So no guarantee, right? But of course, there can never be complete guarantee. Not even humans can guarantee complete success, right? If you ask me to identify a number, well, depending on how it's written and how small it is and so on, maybe, well, this is like when we go to the optics in order to determine what is the grading we need in our glasses. You see at a given point, you say, well, do you see well? Yes, more or less, but I will not be able to tell you whether this E is oriented to the top or is oriented to the left, because at a given level of precision, you lose detail, you lose certainty, okay? Very good. This is how it was done. But why this approach has any chance of success? So this is very much based on what is called the theorem of universal approximation. So you see, this paper by one of those that is very much cited in this context is due to Sivenko, 89. And you see, the paper was published in this journal, Math, Control, Signals and Systems. So this journal, I think, was the issue number 2 of this journal. So it was the first year of the birth of that journal. That journal, I think, was launched by Jan Willens and Eduardo Sontag, two well-known leading figures in mathematical control theory. And this is why, the title is Mathematics of Control, Signals and Systems. Of course, by then, concepts like machine learning and artificial intelligence were not so well coined, or the contours were not so well defined. But for some reason, this paper by Sivenko, which is one of the most quoted papers for the universal approximation property of neural networks, was published in this journal devoted to control. So you see that control was really at the origin of machine learning and artificial intelligence. Actually, I will say probably that machine learning is like the new version, the upgrade of control for the present society of technology and information. So what Sivenko said is very easy to understand. Right? So to explain, actually it was a breakthrough. The proof is not very complicated. It's a fantastic exercise for master students in applied analysis. The proof only uses Ham-Banach in a very elementary manner. At least in one space dimension is very easy. In multi-D there is an added argument to be done, but in 1D is very easy. It says the following. Take this answer. So you do the sum from 1 to n. Well, say, well, it's the same as polynomials. I know polynomials are dense. This is Stone by Strass. Or Fourier series are dense. You need to combine more and more trigonometric functions. Of course, for density, n has to go to infinity. And he said, yes, I take the sum from 1 to n, but each of these terms here is representing one of the neurons in my ansatz. In this case, you can think this, this Sivenko ansatz as simply being the first layer here, a very, very tall layer in which I have n neurons, n going possibly towards infinity in order to guarantee approximation properties. And then inside, in each of these terms, you take a sigmoid function. In that case, he was considering this kind of, sinusoidal smooth exponential transition from 0 to 1. So he was considering any continuous function sigma on the real line with asymptote 0 and 1, moving from 0 to 1, like this, like a front of a traveling wave. Okay, he said this. So you give me any sigma, and I build this kind of linear combination. But I need, for every term in this sum, I need 3 coefficients, alpha, y, and theta. So alpha is very natural. I mean, it's like when you do finite elements. That will be another example. Finite elements are also dense. What do? You take basis functions, can be the triangular functions in Py in finite elements, and each of these basis functions you weight it with an alpha, and then you cook the sum of alpha times this basis function. So you need the alphas, of course, as usual, or in polynomials. Polynomials is just combination of monomials, but in every monomial you weight it. So you have an x to the power n plus an minus 1 x to the power n minus 1 and so on. Okay? In trigonometric functions, the same. You have to weight differently every frequency, every sinusoidal with different frequencies. Okay, fantastic. But then he needs two more parameters, y and theta. Theta is what? Is a translation. So you allow this activation function, the sigmoid, to be placed either to the left or to the right, to move in the Euclidean space where you are evolving. And you also need this scaling parameter y that will either accentuate or relax the concentration. Of course, when you scale this kind of sigmoid activation function with the y, you will either make this ramp to be milder or to be more concentrated up to the point that this ramp will become the Heaviside function, 0 to one side and 1 to the other. And of course, when you are in the multidimensional context, this y transport x denotes the scalar product of a vector y with a vector x. Therefore, this means also that you are also orienting in a space the direction of this ramp. Okay, so you are regulating the direction in which this wave is oriented in a space. So he said, listen, if you allow me to employ this fixed sigmoid function sigma, you let me take n very large, and you let me choose the parameters alpha, y, and theta properly, I can approximate any function. This is what he said. So this is what is called the theorem of universal approximation, which for mathematicians simply means density. Okay? So, well, in some sense, 89, this was a new density result. We knew many before, Stone-Weierstrass polynomial, Fourier series, finite element approximations in many different ways, Galerkin. I mean, there are many, many other approximations you could think of. This was a new family of approximating finite dimensional, say, manifolds to approximate general functions. And this approximation theorem can be established in L1, in L2, in LP, in C0, in Sobolev spaces, and so on. Okay? Now, two things. The first one, key observation. It is true that this looks very similar to classical approximation paradigms, but it's different because I'm not only employing the coefficient alpha to weight each of the contributions, but I am also playing non-linearly with the coefficients y and theta. So because sigma is nonlinear, the way the output of this expression here, of this ansatz, depends on the parameters y and theta is non-linear. Therefore, this ansatz belongs to the class of non-linear approximation models or theory. It's not a linear approximation model as it is polynomial, Fourier, or finite elements. So it's non-linear, and therefore, even if you are able to prove, as can be done easily by using Hahn-Banach, that this class of functions here is dense, now if I ask you, okay, now you know it's dense, okay, fine. So you want to approximate the function f of x, fine. And I give you an epsilon, fine. Now you have to tell me what is capital N alpha, y, and theta so that this ansatz is epsilon close to the function f of x? Well, of course, you need to take n, capital N large. You need many terms to get epsilon close. Okay, I let you take n very large. Take the n you like. But once you take the n you like, now you have to still compute alpha, y, and theta. How are you going to do it? Well, typically you will use a least square approximation. You will say I fix n equal 1 million, many neurons, and I minimize the distance from this ansatz to the function f, say in L2 square. I minimize this, aiming to guarantee that this distance is less than epsilon. I minimize with respect to the parameters alpha, y, and theta. But warning, as I said before, because this is non-linearly dependent on y and theta, this problem, even though you minimize error distance in L2 square, is not going to be convex. So computing the minimizer is going to be a challenge. So this is something you have to be aware of. Nonlinear approximation theory is fantastic because it's very adaptive and it allows you to prove very pretty universal approximation theorems as in this paper by Sivenko. But be careful, the numerical implementation is not like in linear approximation theory. In linear approximation theory, you do finite elements, you have the bases, you are only looking for the alphas. The alphas is just a projection, it's a linear problem. You just compute the coefficients out of the rigidity and mass matrices solving linear algebra problems. So here is a non-convex optimization problem. So again, the best you can do is to apply some stochastic gradient descent. You will get some alphas, some y's, and some thetas, but you will never know 100% whether this is the best ones, whether they are really getting to the epsilon distance you were expecting, and so on. So you have to relax your working context and let it be probabilistic, not really deterministic. So this is the first warning. This is nonlinear approximation theory. Therefore, the practical implementation obliges you to face the challenge of non-convexity and also the one of high dimensionality when capital N is large. So note that here, if we are dealing with scalar functions, alpha is an scalar, but if x is in Rd, d being the space dimension, y lives in Rd, so per each of the terms here, there are d plus 1, so there are d plus 2 times n coefficients to be optimized in a non-convex optimization manner. So if the dimension d is large, as it happens in very many applications of image processing and machine learning, right? What is the dimension of the text in the El Quijote? Huge, right? How many words, how many phrases, how many different interpretations of these combinations of words and phrases. So the dimension is huge. D is huge. Therefore, there are in each of these n neurons, there are d plus 2 coefficients. You are certainly working in a non-convex high dimensional context, so warning here. And the second one, the second comment I wanted to make is that this result that was so impactful and apparently new, in fact, when you look to this paper by Norbert Wiener back in 32, 100 pages in Annals of Mathematics, probably it was the PhD thesis of Norbert Wiener, I don't know. The title is Tauberian Theorems. What you see is that Norbert Wiener does the same, but instead of using these sigmoid functions, he uses the Gaussian. Actually, what Norbert Wiener does at that time, Norbert Wiener was not employing the Y. Norbert Wiener was not employing the scaling. He was just thinking, what are the basis functions? It turned out that Gaussian is a good answer. But what are the functions sigma in general so that whenever I do linear combinations of translations with theta of this profile basis function, I will get a dense set. And then Norbert Wiener used the Fourier transform to say, listen, a good sufficient condition for these ansatz to be dense without the employment of the y, only the alpha and the theta, a good sufficient condition for this to be dense is that the Fourier transform of the basis function is non-zero everywhere. What is a good candidate of a function so that its Fourier transform is never zero? Well, it's the Gaussian, because the Fourier transform of the Gaussian is the Gaussian. So you can, this is an oversimplification, but we could say that Norbert Wiener was doing the same as Sivenko without using the y, employing Gaussians, and that Sivenko did the adaptation to these kind of sigmoid functions, right? But to the price of employing also the scaling parameter y. Now, in this sigmoid function, could we apply Norbert Wiener? No. I mean, you know that what is the Fourier transform of this kind of shape function, this sigmoid function? What is the Fourier transform? Well, it can be computed by hand in some simple cases, but think, for instance, on the limit case where the slope of this sigmoid function becomes infinity and you get the heavy side. The heavy side is what? The heavy side is the primitive of the Dirac delta. The Dirac delta, right, has as Fourier transform the constant one. But the primitive, then you pay xc. So you see there will be certainly a sign change in the Fourier transform of this kind of sigmoid functions. So this is why Sivenko could not employ Wiener, because the Fourier transform of the sigmoid function was not fulfilling the condition of Wiener of having a Fourier transform that is non-zero everywhere. But he could compensate this by the use of the y. And he probably thought, well, listen, already the ansatz of Wiener is nonlinear. Because even if you don't use the y, because you are using the theta and the basis function sigma, the Gaussian is nonlinear, this is a nonlinear approximation paradigm. So I remain nonlinear, I employ the y, but I am able to use the sigmoid. And why Sivenko thought the sigmoid was better for neural networks and machine learning than the Gaussian is because somehow the sigmoid, right, which is 0 to one side and 1 to the other, better mimics the functioning of the brain, in which we activate some neurons, right, 1, while some others are kept inactive, 0. So this kind of sigmoid function is better adapted to this sparsity, in which some of the neurons that are present of the system are passive while the other ones are active. Some of them are turned off while the others are turned on. Nowadays, one of the functions that is more used, as I mentioned before, is this ReLU on the top, which is kind of oversimplification of this sigmoid function that is moving from 0 to 1 in a smooth manner. The ReLU simply does it basically in a bank manner. You could say, well, instead of the ReLU, I could use the Heaviside function 0, 1. Well, yes, but the problem is that the Heaviside function, you cannot differentiate it, and therefore it will be hard to employ, for any kind of stability analysis. Needless to say, is not differentiable. So for training, for applying gradient descent, computing directional derivatives, for sensitivity calculus is very hard. So instead of thinking on the Heaviside function, people said, what is the Lipschitz function that is the closest to the Heaviside function? Well, it's the ReLU. Okay. So this is a very brief revision of the theorems of universal approximation that led to the revolution in machine learning. Now, let me comment on something that I think historically is relevant. You see, in Wiener published his paper in 32. Sivenko publishes his paper in 89. So 59 years, at least 2 generations of mathematicians, right? So with this gap, certainly Norbert Wiener could not be the PhD advisor of Sivenko. At most, Wiener was the PhD advisor of someone who was the PhD advisor. So, there are 2 generations of mathematicians gap, 60 years gap. Why so long, in your opinion? What happened in the 80s that didn't happen before? Well, in the 80s, computers arrived, personal computers arrived. Until the 80s, personal computers were very rare. Desk computers, actually, not portable. Desk computers were very rare. So it was the fact that plenty of computational resources were made universally available that people started to take seriously these ideas that were already initiated by Norbert Wiener. Yeah, I mean, it was a great paper, Norbert Wiener. It was published in the Annals of Mathematics, 100 pages, Tauberian theorems, but probably people were thinking, but what is the use of this? This is certainly a beautiful mathematical analysis. You link the Fourier transform and then the translations and a different way of dealing with density of functions. But what is the use? Who could use that? It was a nonlinear approximation theory. Nobody could use that. People were already satisfied by employing, the very first steps of the theory of finite elements and so on. So it took 59 years in some sense because it is when people experience the possibility of employing these new techniques. And it's when this possibility emerged that people went back to this topic and said, listen, maybe after all, it's time to go back to the old paper by our old friend Norbert Wiener and see what can we do with all these universal approximation theorems. Nowadays, I will go back to this. When we see neural networks operating, you see things like this. Actually, what is what here? So in this video to the right, I have shown you this is just a plot, a video plot of a deep neural network that is classifying, tennis balls, the yellow ones, the green ones, and the purple ones. So this deep neural network has been trained, as I told you before, in order to learn that the yellow tennis balls have to go to one basket, the one here. The purple ones have to go to a different basket, and the green ones have to go into a different basket. So this deep neural network that here I have represented in a video, because of course this becomes a time discrete dynamical system, but the video representation of a time discrete dynamical system looks like a continuous in time dynamical system. Each of these tennis balls that I put in the initial layer at random, right? I throw a ball to this neural network. This neural network has been trained to distinguish colors and be able to bring each of the ball to the corresponding labels. This is actually something that your computer does in your photos folder. You go to the photo folder, maybe you have 10,000 photos on it, totally disordered, and you want to put order on them. You can try to do it by hand. I mean, you are welcome. It will take you forever. You will never finish. So you better go to the photo folder, you open a few photos, you allocate names to the different people in your photo folder, and then let the computer do it automatically. By pattern recognition, it will create the folder of, your father, your mother, your brother, your sister, your partner, your daughter, your son, okay, your friends, your colleagues, and you will get a photo folder per person, and you will see that this is done very, very successfully, and very rarely you will find errors. So automatically the machine will generate folders where you will see in the yellow basket the yellow tennis balls, or in one folder your own photos, in the other folder the photos of your partner, the same. This new deep neural network was able, after training, to well recognize the different colors of the tennis balls and bring the yellows to the yellow basket, the purple to the purple basket, and the green to the green basket. Okay? So on the right-hand side, you see supervised deep learning. Deep because there are many layers, and this is why I see a video, is supervised deep learning. On the left, it looked very similar. There are these red dots evolving. But there are also some 4 blue dots here developing this very complex dynamic pattern that produces that the red dots evolve from the initial configuration to the end. This, on the left, is a control problem. So this is dogs and sheep. There are 4 dogs in blue herding a flock of sheep. So this is a classical control application in animal behavior. The relation between dog and sheep is asymmetric. The dog runs after the sheep. The dogs like to be close to the sheep, while the sheep are afraid of dogs. They escape the dogs. And therefore, the dogs, when dancing in this, smart oscillatory manner, they, as you see, they develop this they create a kind of diagonal corridor along which the sheep escape, and without noticing, they get into the gate. So if you see the video on the left, you say, well, this is control theory. Why? Because I needed to compute a priori the trajectory of these dogs. This is open loop control, dogs in blue, developing this control pattern, which successfully brings sheep from the initial position to the gate, where they have to spend the night to be safe and not to be, attacked by wolves. Okay? So this was control. When you see the video on the right, you say, well, this is nothing to do with control theory. This is deep supervised learning. My point is that these two things are the same. Now, maybe if I try to convey this, you will tell me, well, but where are the dogs here on the right? On the right, there are no dogs. There are only yellow sheep, green sheep, purple sheep that go to 3 different gates to spend the night. But I don't see the dogs. Where are the dogs? Where the dogs are these coefficients. The dogs are these coefficients that I have pre-trained, I have pre-computed, like, so the A's, the W's, and the B's that I have pre-computed for every neuron, they really play the role of the controls. Except that in the context of machine learning, nobody asks, right? When you see the magnificent performance of ChatGPT, nobody will tell you, oh, but what are the parameters? What are the values of the parameters of ChatGPT? We already had enough by knowing that there were 175 billion parameters. But these parameters have been pre-computed. We can see them as a time discrete version of time continuous controls for a control problem these parameters have been pre-computed the same way as controls are computed when we are doing open loop control in a pre-manner. This is why we say pre-train. We pre-compute, we compute the controls offline. So, after all, supervised learning is very much like open loop control in control sciences. So there is a very clear analogy between the two fields. And actually, when you want to bridge them, there is a very nice model that does this. So you see the model at the bottom is Sivenko. You can say also Wiener, 57 years before, right? So Sivenko in 89 or Wiener in 32. This is their perspective. It's purely static. You give me a function of x, and I approximate this function of x by an answer like this. Now, before I was calling it n, now I call it k, and the names of the parameters have changed, but it's the same answers. Sigma, from now on, I will typically think, as in modern times of machine learning, as being this ReLU function. But you could think on the sigmoid function of Sivenko or the Gaussian function of Wiener as well. Okay? But this is the static perspective. Now, as we know, in a static manner, it will be very hard for all of us to figure out what is the shape of this function. How can I train all these parameters in one shot? This is why people thought of dealing with recurrent neural networks, or even this simplified version of recurrent neural networks, which is the residual neural network, in which, each of these parameters, W, A, and B, are entering gradually, step by step, along a time discrete iteration. So this is, Sivenko will be depth equal to one single layer, and very tall, very high width, eventually going to infinity as k goes to infinity, while in these residual neural networks is the case where the neural network is very, very deep, because you might eventually do many, many iterations with k, so k will be the depth, very, very, very deep, but very, very small width. I think this is what is called shallow, like in shallow water, because the width is very narrow, right? Is shallow but deep neural networks. And once you have written this time discrete version of this exercise that in the classical ansatz of Wiener and Sivenko had to be done in one shot, once you have written this in this time discrete fashion, you immediately realize that this is nothing but the time discrete version of this time continuous neural differential equation, okay, that we will call neural ordinary differential equation. Once you write these neural differential equations, you realize that you are on the boat. Why? Because now this is a differential equation. It's nonlinear because there is a nonlinear activation function sigma on it. But the nonlinearity sigma is globally Lipschitz, so you can apply Cauchy-Lipschitz. There is existence and uniqueness and stability estimates a la Grunwald for the solutions of this system. And then the parameters W that before were depending on this discrete parameter K or this index J now depend continuously on T. WT, AT, BT are nonlinear control functions depending on time. So this becomes a nonlinear control problem. So we are on the boat. We don't even need PDE control theory. This is control of ordinary differential equations. So control of differential equations, nonlinear differential equations, should serve at least to some extent to explain this incredible success of machine learning. Now, when you watch the second video, the video to the right, when you see the video to the right, you see that there is a big difference from classical control problems to the control problem I am solving here. Why? Because in classical control problems, like, when Potriagin was considering this, the control of these space missions in which the rocket had to go from Earth to the moon, right? This is control of a finite dimensional trajectory on a long time horizon from origin to destination. In the classical paradigm of control theory, you give me an initial position, you give me a final destination, and I compute the control so that the trajectory goes from initial position to the destination, like an airplane traveling from maybe Seville to Nuremberg, right? So that next time, you can visit us and take the course here, right? Instead of doing it online. So typically is one airplane or one rocket, one particle from origin to destination with the suitable controls. Here, in the context of machine learning, we are bringing all data simultaneously from the initial configuration to the destination. So this is a giant simultaneous or ensemble control problem. Jacques-Louis Lyons used to call these simultaneous control problems. Brocket rather was using the terminology of ensemble, because you are, controlling a cloud of points simultaneously. And this is what I represent here, right? In this plot in which you see plenty of red dots and blue dots, plenty of red tennis balls and blue tennis balls. What you want is a dynamical system that will bring all these tennis balls simultaneously along the flow. Once you have computed the controls W, A, and B to fulfill this simultaneous or ensemble control task successfully, is bringing each of these balls either to the red basket or to the blue basket. Okay? Very good. Of course, if you believe that this can be done, and once, as you will see, we can understand why indeed control theory helps understanding the success of this deep learning through this toy model of the neural differential equation. When you want to get into, real the depth of machine learning, you will realize that there is an infinite amount of work to do, in particular that because there are so many different architectures that people have developed for the different neural network tasks and machine learning tasks, that each of them will require a specific analysis. So here we are dealing with the simplest architecture in which the width of the network is fixed. I make it deep, so we have this horizontal strip along which information is evolving. And this is the one that either with one neuron or with several neurons is better adapted to be understood through this model of neural differential equations. Okay? So now, in ChatGPT, there is another, so this is what is called the transformers. The transformers is an architecture, is also explained in these videos in 3 blue, 1 brown. The transformers is this architecture in which not only you combine these layers in which information is being transferred from one layer to another by tuning the parameters, but the efficiency is accelerated. The efficiency of learning is accelerated by some intermediate layers that are called attention, which have the goal of clustering information as much as you can. So as you will see very soon, once we see why machine learning works, you realize immediately that, machine learning will certainly benefit, the task of machine learning will benefit from clustering. Actually, you can even see it in this drawing here, right? Assume that instead of having to do it with a complicated neural differential equation and using control theory, you will tell me, Enrique, this is the configuration of the tennis balls in the field. Please put order on them. Bring all the blue to the blue basket and all the red to the red basket. So I will get to the field and I will say, well, there is plenty of work to be done, but it's not that bad. You see why? Because, for instance, all these blues are on a cluster. So I could take with the two hands, I could take all this cluster on one shot. And in one shot, I will be able to carry on the 20-something balls in this cluster to the corresponding blue basket in one shot, as if it was just a big ball. So you see that somehow the complexity of the problem reduces by clustering. 25 blue balls. When together, they can be treated just like a one big blue ball, and therefore, at the level of classification, at the level of learning, it can be treated as a unit, reducing significantly the complexity of the learning process. This is why the transformers have got so far, and they are able to deal with such a giant architectures, and they are able to read the Bible and Quixote and all other books, is because they are endowed with these extra algorithms and tools of the attention mechanism that plays the role of packing information and trying to generate clusters in order to reduce complexity. I will mention this in some more detail later. Okay, this is something we have seen, the complexity. This is the bridge, right? The bridge linking control and machine learning that motivates the title of our lectures here. These are some papers we have written in that topic. Maybe the one that I can recommend you first is this Siam News article that you can find freely online, published 2 years ago, and in which, in a couple of pages, in a dissemination style, we describe the very elementary ideas I have introduced you now about the links between machine learning and controls. Okay, very good. Now, in the last 2 minutes, I just wanted to go back to Norbert Wiener again. So you see, Norbert Wiener, in 32, he writes this huge paper, 100 pages in analysis of mathematics, about nonlinear approximation theory, functional analysis, Fourier analysis, very beautiful. 16 years later, he was writing his book in cybernetics. That was the name that was coined by Ampere and then, forgotten. And then Norbert Wiener rescued that terminology. He coined again this term. He reshaped the term. He gave it a meaning. And he defined cybernetics when referring to control sciences, control engineering, mathematical control, as the science of control and communication in animals and machines. So Wiener, the one who proved the first theorem of universal approximation, 16 years later, he was working in control theory, and he was defining control as the science of communication and control in animals and machines. And now when you read this definition again, and if I tell you that this is very much the definition of machine learning, you will probably agree. It is certainly about machines doing the work of animals, in this case humans, right? Based on communication, on learning, on reading, on, right, supervised learning, on data, on communication, and control as the exercise of pre-training the parameters by optimizing them. Okay, so we will start here at this point tomorrow, and we can then evolve little by little, getting more into the maths of the topic. Thank you for your attention.